Hi everyone, I'm Anil Anadi. Today I'm going to present the quantized conductance that we have seen in quantum point contacts embedded in LAOSTO nanowires. This work is done at University of Pittsburgh and Professor Jeremy's lab. Here I would like to acknowledge our funding agencies for financial support for this work. Our working system is LAOSTO oxide interface, which is known for novel phenomena at the interface, such as high mobility electron gas and superconductivity magnetism at the interface. The system also possesses sharp insulator to metal transition at about 3 layers of LAO on STO, and this insulating 3-unit cell LAO STO sample can be made into conducting by applying a positive voltage to the interface through strontium titanate. Exploiting this insulator to metal transition, in our group, it was first shown that when a positive voltage applied to the AFM tip and the interface becomes conducting. I'm going to discuss the writing process in coming slides. The nanowires made with this writing technique have shown enhanced mobility compared to the bulk 2D electron interface LAOSTO system. Further, recently we also made devices that resembles a quantum dot, and these devices shown single electron transistor behavior, and also we have found a new mechanism called electron pairing above the superconducting regime, and also these devices shown Fabry-Perot interference. These results will be presented in these sessions. We further wanted to investigate the ballistic nature in these nanowire devices, that how far these electrons transport without scattering. We believe this is very important for realizing exotic phenomena such as quantum Hall effect and edge states in LAOSTO based devices. One need to investigate or make one-dimensional structures such as nanowires and quantum point contacts to study the ballistic nature of transport. An example shown here, a constricted aluminum gallium arsenide interface system, where when the electrons were allowed to pass through a nanoconstriction, in these devices the conductance gets quantized to the 2e square over h quantum value, and this depends on number of modes passing through the device. So we wanted to make and investigate the nanoconstriction and its behavior in LAOSTO nanowires. We feel the additional degrees of freedom such as superconductivity, spin-orbit coupling and magnetism in the LAOSTO interface further makes it interesting. So this is our device writing geometry and writing process, where we use 3-unit cell LAOSTO interface as a platform, and we make first the connecting leads to the gold electrode by applying a positive voltage and writing nanowires. And this is our active device geometry, which is having an 80 nanometer length, and in this nanowire we put 2 weakly insulating barriers applied by negative voltage to the tip. This is our active device writing process, where we first write a nanowire by applying a positive voltage to the tip, and on top of it, as I said, we apply two short and negative voltage pulses in this active device structure, and this would eventually acting as a quantum point contact, as I will show in coming slides. So this is our measurement geometry, which is a 4-terminal measurement, and the below figure shows the tunability of our device with respect to the side gate, where for the negative side gate values the device completely pinched off, and we further measure the source drain bias sweep in these nanoconstriction devices. At the 0 Tesla magnetic field and 50 millikelvin, we obtain conductance with respect to the side gate values, and near zero bias we see interesting features. Below figure shows the zero bias conductance of the graph, where the conductance increases non-monotonically, and it appears that it also has a plateaus. This at specific values and also having some resonances in this device. When we applied a magnetic field out of plane to 9 Tesla, so these conductance appears to quantize to certain values, appears to integer values of E square over H. This says that we further measure the magnetic field dependence of zero bias conductance. Here are the sequence of conductance plots obtained at various magnetic fields. At low magnetic fields, it appears that plateaus are near to the 2 E square over H values, whereas at a higher magnetic fields, they're precisely at 1 E square over H values. To further visualize the data better, we extracted transconductance by performing derivative of the conductance. Here is the 2D plot, and here the color scale represents the transconductance. It appears that the first plateau splits from the second plateau, whereas the third plateau splits from the fourth plateau, and the splitting happens at critical magnetic field, and also we see at times the crossing of these arms in the transconductance data. We analyze the data considering the Zeeman splitting in the system. Imagine that in absence of magnetic field, the spin up and spin down levels correspond to the first subband or degenerate in absence of magnetic field, and when the chemical potential of the device is somewhere here, one would expect to see 2 E square over H value, whereas in the presence of magnetic field, the spin degeneracy is lifted and this up and down levels of spin or splits with respect to each other, and when the chemical potential of the device is such a way that one would expect to see 1 E square over H, 2 E square over H upon raising the source gate voltage, and the splitting strength depends on the G factor of the device and also magnetic field strength. To extract the G factor for this subband splitting, we analyze the transconductance data further near the first plateau, and the splitting energy can be extracted by measuring the spacing between these two arm joining points. Basically, the splitting corresponds to when the chemical potential of the device matches to the bottom of the up and down spin subbands. So we extracted this delta E for various magnetic fields, and we plotted here it up. The splitting energy is about 30 microelectron volt per Tesla, and the slope gives you the Z factor is about 0.5 in this device. We further measure the temperature dependence of the device to see how far we see the plateaus with respect to the temperature. We see these plateau structures up to 700 millikelvin, which is corresponds to the 60 microelectron volt thermal energy. Since the energy is in the range of our measured subband splitting energy, so above this energy the plateaus smeared out because of the thermal activation energy. So we further made the longer devices to see how far these electron transport in these devices without scattering, and in a device made with a length of 600 nanometer, we still see a quantized conductance at 9 Tesla, even up to 2 subbands. So this data is very interesting, significant, because it appears that even though the quantization happens in this constricted regime, the electrons transport without scattering even in the devices of 600 nanometer, which shows that ballistic transport in these devices above the scattering length of the device. To summarize my talk, we successfully made quantum point contact devices embedded in LAO-STO nanowire devices, and the integer conductance quantization that is seen at 9 Tesla implies that the possible spin polarized transport in these devices at higher magnetic fields. And we have seen the conductance quantization in these devices of length as long as 600 nanometers. So thank you very much.